All right, section 2, coordinate systems and vector components. So finally, we're going to officially talk about vector components. I've kind of talked about it a little bit already, but now we're going to officially talk about it. So we want to break a vector that's at an angle to an axis into its components. So the components are going to help us analyze the vector that's at an angle. And so I'm talking about the parallelogram rule here, but I generally, after this, I really don't talk about the parallelogram rule. We just break it into components that are parallel to the axis or axes. And it helps us work with what we're dealing with. So if this vector A here is our original vector, then we want to break that vector into x components and an x component and a y component. So here is our x component here. And here is our y component here from the original vector. And if you use the parallelogram rule, you can see that I could take this a sub y vector and move it over here to form a right triangle. And I could instead take this vector a sub x and move it up here to form this right triangle here instead, okay? And what I've created is a parallelogram. Right? It's actually a rectangle, a little bit more specific, but this is following the parallelogram rule. More important than that, because we are our component vectors are parallel to the axes, so we've created a right triangle, two right triangles. We've created a rectangle, but most important of all, we've created two right triangles here. So it just depends on which right triangle you want to create, and that will dictate which a sub x and which a sub y you want to create here. So let me get rid of a couple of these so that it's not as complicated looking. So this a sub x here that I left on the drawing, and this a sub y here, maybe that's the one that I want for whatever reason in that particular problem. It just makes sense to have those two on there, okay? Maybe it makes sense to have the original ones that they put on there, so maybe that vector there doesn't make sense, and maybe I actually want to leave it like that, okay? But when you break your vectors into components, you want to decide, like first, where do I want to put my a sub x and my a sub y? Based on how my vector A is and how the problem is being set up, okay? Generally, though, we want to create some sort of right triangle because it makes sense to do that. When we break our vector into components, we're going to want to use trig and the angle that's maybe sitting right here to help us decide how long that vector is using like sine and cosine or maybe tangent, depending on the information that we have. All right, so the sign of the component vectors is going to follow the conventions of our normal coordinate system. So our normal coordinate system would be positive if we're pointing in the positive direction, negative if they point in the negative direction, just depending on how you decided to set up your coordinate system. So if we set up our coordinate system with positive x to the right and positive y up, then like we've been doing, then we know which way is positive, which way is negative. Use subscripts to denote the components. So if we have vector A sub x, A sub y, vector B sub x, B sub y, and so on, okay? So in this case, we have our vector A like that. Then A sub y has this magnitude right here. Notice that those line up like this, okay? And they're saying here A sub y has a magnitude of 2 because its length right here is 2. And a sub x has a magnitude here of whatever this length right here is, and notice that those line up right there, okay? So that magnitude is 3. B sub y, so we're on vector B now. B sub y has a magnitude of 2, because its length is 2. But B sub x's magnitude is 2 as well, but its direction is actually, it's pointing in the negative direction. So the vector B sub x is negative 2 meters. So now we have this vector C. Notice the direction. Okay, I'm doing a horrible job of drawing that, so I'm just going to get rid of it. And the vector c with that direction, c sub x here, is pointing in the positive direction. So it's the magnitude is the magnitude, but the direction is positive. So c sub x is a positive 4 meters. The magnitude for c sub y would be positive, but because the direction is negative, then c sub y, the component, is negative 3 meters. Okay? So now how would I find the length of, let's say, just the length of vector c?
Vector C,
Yeah.
distance formula, yeah.
Or
Slope.
I could do the distance formula, or I could do what?
Would it be slope?
No, that wouldn't, we're not talking about slope. We just want the length of vector c.
Pythagorean theorem.
The Pythagorean theorem, actually the Pythagorean theorem and the distance formula are exactly the same thing.
Oh, yeah.
So the length of vector c would look like this, just the magnitude, that's all I want, okay? So that would be the square root of c sub x squared plus c sub y squared. It's just the Pythagorean theorem. Okay, so c sub x is 4 squared, 16, plus c sub y, which was negative 3, but I square that and I get positive 9. So
5.
that's 25, square root of 25.
5.
So the magnitude of the vector c is 5. Okay? We didn't find the direction, we don't know what the direction is, but the magnitude is 5. All right? All right. So next, finding the components of the vector. So this is where we have the original vector and we're breaking the vector into its components. So like a sub x and a sub y. So here we have an angle. The angle is theta. The magnitude of the original vector is a. Okay? So it has some length a. We don't know what it is, which is fine. The components are a sub x. So a sub x would be along the x direction out to the side there, and a sub y then would be coming up to, so like almost tip to tail, right? Forming that right triangle. So a sub x, notice the cosine angle right here is, the angle right here is theta, so this is the adjacent side. This is the hypotenuse now, because it's across from the right angle. So adjacent and hypotenuse is what we could use. So therefore, we would have, let me, off to the side, we have cosine theta equals the adjacent side, which is a sub x, over the hypotenuse, which is a. And if I'm looking for a sub x, then I'd multiply both sides by a, and I wind up with a sub x equals a cosine theta. That's where that came from. Now, if I want to find a sub y, my reference angle theta is sitting right there that I scribbled all over, is across from, so that's the opposite side, and I know the adjacent side, the original vector a, so I would use sine. Sine theta equals the opposite side, a sub y, over the hypotenuse, which is a. And now if I want to solve for a sub y, I multiply both sides by a, and I wind up with that formula right there. That's where those come from. Okay? So we're going to be using trig a lot to help us come up with what the components are on the triangle that we're looking at. When we set up, when we break apart our original vector into components, a sub x and a sub y. And it's helpful to think about like the SOHCAHTOA acronym that we deal with so that we can look at what we have and then set up which cosine or sine we're going to be using. Okay? Now, so I'm telling you, you must draw a picture. You absolutely need to draw a picture to understand how the angles are working in each situation, so you can understand how the vector components are going to be defined. If you don't have a picture, you're not going to know for sure, and most likely you're going to come up with the wrong answer. So, specify the vector from its components. So in this case, we have our vector. We're setting up our a sub x here. We're setting up our a sub y here. That forms the right triangle there. That makes our vector the hypotenuse. And then a sub x here with our angle sitting right there, our reference angle. That makes a sub x the adjacent side and a sub y the opposite side. So we'll be using sine for a sub y and cosine for a sub x. Notice that we can also use tangent. Tangent would be opposite over adjacent, so that would be a sub y over a sub x. Oops, tangent theta. Okay? Now, normally we don't use tangent because normally we don't have one of these sides. Normally we have the hypotenuse. So normally we're going to use sine or cosine to come up with the sides themselves. Okay, but if we did have one of the sides and we're looking for the other side, then we'd use tangent. Okay, so the relationships for a vector with a negative component. So in this case, we have a vector component, we have a vector that's kind of going down and to the right here. So we have our reference angle that we set up, so we're dropping our y component down, and our x component is going across to the right. So our x component is positive, our y component is negative. So we got to keep that in mind. So in this case, our reference angle is right here. Our right angle is right here, so the vector itself is the hypotenuse. So if I want to come up with my x component, the reference angle is across from the x component, so that makes it the opposite side. So that means I would use sine, and then they're using a different symbol for the angle. It's okay, you can use theta, it doesn't matter, okay? So sine theta equals the opposite side, which is my x component, c sub x, over the hypotenuse, which is c. So then c sub x equals c sine theta. Okay? So notice this time the x component is using sine. All right? That's why you got to draw the picture. You can't assume it was a formula that's always going to be true. Okay? Draw the picture. Then for this one, for the c sub y component, this is the adjacent side that we're talking about here. So that means we have the adjacent side that we're looking for. We know the hypotenuse. That was the vector that we were talking about in the first place. So that's cosine. Theta equals c sub y, the adjacent side, over the original vector c. And now when I solve for c sub y, I get what they have written right here. Okay? But we have to remember the orientation of our coordinate system. This vector is pointed down, which is against the positive, so that means we have to say it's a negative component, okay? So you always have to keep in mind, what direction is this vector going? Oh, I gotta make it negative, okay? Because the math isn't gonna do that for you. All right, so we're gonna practice. We want to find the x and y components of the acceleration vector A that's shown here. So what are we going to do?
Show our lines left and down. Our vectors.
Yeah, so break the vector into components. So we have a y component going like this, and an x component going like that, and a y component going down. And it doesn't matter if I drew it the other way. I could have drawn the y component over here and the x component going this way. Either way, it doesn't matter. Why did I choose to draw it like that?
Because it's on the axis.
Well, the other way, we would have had the other vector on the axis.
Tip to tail.
It would have still been tip to tail. because the angle was given right there. So I incorporated the angle into my components that way, okay? So it just made sense to do it that way. Okay, so now I gotta break into components. I see the components. What is this one along the axis here?
A sub x.
This is a sub x, and then this one is a sub y. Okay, now these are vectors, so we put arrows over them. And now we just gotta figure out what their lengths are. How do we do that?
A sub y is the opposite and hypotenuse, so that's so.
Okay.
So sine
Okay, so we're gonna go sine
30
30 degrees equals,
a sub y over 6.0 meters a second.
okay, over a.
Yeah, over a. Sorry.
All right, so then I could have said theta here instead of 30 degrees since we're using letters right now. Okay, so then I solve for a sub y, which means I gotta multiply by a. So I have a sub y equals a sine 30 degrees. So a is 6 meters per second squared, sine 30 degrees. If you know what sine 30 degrees is, you might not need a calculator, but if you do, then fine. What do you get? Make sure your calculator's in degree mode.
Oh, okay. How do you change? Oh, no.
Listen, I wish I would have had my ACT questions I did this year last year. Everything was probability.
Oh yeah?
Everything.
3.
3 what?
3.
3, just 3?
3 flat.
Just 3.
It says I put 6 times
Yeah.
sine 30.
But your calculator doesn't know what you're doing.
Okay, so parentheses.
So you know, you gotta tell me what the answer is.
Oh, 3 meters second squared.
Okay, that's it? Just 3?
It says here. I'll try to.
I know what it says. But now you gotta be smarter than the calculator, because we're doing a problem that it doesn't understand. So, am I just writing 3?
3.0.
Meters is
3.0,
0
because we have 2 significant figures.
3.0 meters per second squared.
Okay, now is this right?
No. Or is it just meters per second?
It is meters per second squared. That part's right. I like the 3.0, but we're not right.
The degree.
It's not degrees. It's
Oh,
meters per
wait,
second
it's
squared.
negative.
It's negative. Why is it negative?
Because it's going down.
Uh-huh, that component is down. So this is a negative 3.0 meters per second squared. Okay, how about the x component? What do we do?
It's the opposite. Oh, wait, no.
That's the adjacent over
Uh-huh.
hypotenuse.
So cosine.
So it's cosine. Cosine what?
30.
Okay.
Or cosine. You could have been theta.
You could have said theta, yep. Cosine 30 degrees equals what?
A sub x over a.
Okay, now what?
That's that'd be
A cosine 30 equals AX.
Okay, so a sub x equals a cosine 30 degrees. So now we have a is 6.0 meters per second squared. Cosine 30 degrees. Wow.
Negative 5.196.
Okay, negative 5.196.
but because of significant figures,
It's 1.
it'd be negative 5.2
Good, negative 5.2
meters per second.
meters per
squared.
second squared. Nice. That's how you do it.
Doesn't seem terrible.
No, it's not terrible. Okay, next one. What are the x and y components, c sub x and c sub y of this vector? What do we do?
Up and then left.
From here, we're gonna go up and then left, okay. When we went up, that was c sub
Y.
and this is C sub,
X.
okay? So what do you get for C sub Y?
We don't have.
Oh, I went up way too far. Let me redraw this.
We don't have an angle, so it's just
Yeah,
theta.
Okay,
so just theta.
It's 2 centimeters.
for C sub Y?
Mm-hmm.
How do you get that?
Going up to- Oh, that's how we find it.
Yeah.
Oh, okay.
We have a grid here, we can count, right? What's C sub X? What?
Negative 4.
Okay, good. -4 centimeters. All right, that was an easy one. Now, we can add vectors graphically, which is what we just did. There is an easy way using components as well. If we look at the vector sum C equals A plus B, that's this guy right here. C equals A plus B. All right, so in general, here, I have vector A plus vector B, right? So I look at vector A, and I look at vector B, so graphically, I add those two vectors together, and I get vector C. Now, if I want to do this a little bit better, I can break vector A into components. Vector A sub x, A sub y. Now I can take vector B and break that into components as well. I can go B sub x and B sub y. And in the end, what do I get?
3.
I get vector C. This sum right here will be C sub x, and this sum right here will be C sub y. And if I take this guy right here, and I put it tip to tail right here, I get vector C. Okay?
Oh, okay.
So by breaking those vectors, A and B, into components, A sub x and B sub x, I put them together, I get my vector C sub x. If I take A sub y and B sub y and I put them together, I get my vector component C sub y. And then I put C sub x and C sub y together, and I get my vector C. Okay? It's better than trying to do this right here. Okay? That's the way we actually do it. Vector components. Okay, so in general now at the bottom, if vector D is vector A plus B plus C plus however many other vectors we have to add together, then the x and y components of all of those vectors added together give us the vector components of the resultant vector. So that's what this is saying. D sub x equals A sub x plus B sub x plus C sub x plus however many other sub x's we have to add together. And the same thing is true for D sub y. Add all the y components together, and you're going to get the resultant vectors, D sub x and D sub y. And then you can put those together to make the resultant vector D. Okay? That's a really powerful thing to do. That's called algebraic addition, and that's what we really do when we're adding vectors together. Okay? That's the best way to do it. Okay, so this can also be applied for vector subtraction, vector multiplication, with a scalar, everything. So to find D equals the vectors A minus B, first thing we do is D sub x equals A sub x minus B sub x, D sub y equals A sub y minus B sub y, and then we put them together. Okay? If we want to do some vector T equals a scalar, this C right here is a scalar multiple. We've talked about that before in this class a little bit, but also like in Algebra 2, when you have matrices and you're multiplying a scalar in, you remember that? All the components get multiplied by that scalar. So we just take the vector components, we multiply each component by that scalar, and then we put it back together. Okay? Not tough. Let me just make sure I'm not skipping something. Nope, we're good. Okay. So, here's an example. A bird flies 100 meters due east from a tree, then 200 meters northwest, which means 45 degrees north of west.
Okay.
What is the bird's net displacement? Okay, so what are we going to do?
100 meters to the right, so a vector.
First thing I'm going to do actually is draw axes. Making a map, basically. The bird is going to start at the origin. Where does this bird go?
100 meters that way.
100 meters due east. So you can wind up over here. 100 meters, right there. 100 meters. Okay, now where does the bird go?
200 meters north of us, 45 degrees.
45-degree angle north of west. So we're going to go back 45-degree angles, 200 meters, right? So something like this. To there. This is a 45-degree angle right here. And we're ending up right there. What is the bird's net displacement? What are we looking for?
Oh, you just make a triangle with the rest of it.
Yeah. So from where we started to where we finished, that's the bird's net displacement. What can I call that for net displacement?
A sub y.
No.
C sub y.
No.
Wait, delta.
Is that purely in the x direction or purely in the y direction?
No.
No, this
No.
would be a sub xy.
No.
Would it be delta?
A.
You could call it A, but for displacement, I might use the letter
D.
D. Okay, so that vector is the bird's net displacement. Now, the smart thing to do here, oh, I forgot to label this, 200 meters. So the smart thing to do here is to break the displacement vector into components right away, okay? So the displacement vector becomes from here over to here, d sub x, and up to here, d sub y. Okay, we have a right angle right there. Good so far? Okay. Additionally, what about this vector right here?
A.
A, B. If we call the bird's first move A, then this would be the second move, and we call that B. Okay? So then this would be vector B right here, and this is vector A right here. Okay? Now we can break, since this vector B is at an angle, it's smart to break that one into components as well. Okay? So this would be B sub y, and then this movement is B sub x. And notice what overall shape I just made.
A rectangle.
A giant rectangle. Okay? By breaking up those vectors that are at angles, now I have this giant rectangle shape. Okay? Now, right now, I don't know anything about d sub x or d sub y, but I can find out because I have this right angle right here, and I know the vector b. Okay? So what I want to do is find out things that I need to know about this spot over here by finding out b sub y and b sub x. I have to know that length b sub x, because once I find out b sub x, I'll know d sub x. You see? And I have to find out b sub y, because once I find that out, I'll know d sub y. Right? Okay. And once I know d sub x and d sub y, what will I be able to do?
D.
Find d. Okay? So, let's get to work on b sub x. So, d sub x or
No.
b sub x?
We'll find B sub x.
B sub x, okay, how do you wanna find B sub x?
The 45 degrees go to the other angle too, because it's a right angle.
Great, this is also 45, now what?
So then we have the degree and h, it's the opposite and hypotenuse.
So,
That's
what are we
sine.
using?
Sine? Or cosine? So, yeah, so, sine.
okay, sine
Theta
equals
equals bx over b.
over b, okay, then?
Multiplied by b.
So b sub x equals b, which is 200 meters, sine
45.
45 degrees. All right. What do we get?
So 141.
Okay. 141 meters for b sub x.
Meters. Yeah.
All right.
So now we find B sub
Now,
y.
b sub x, though, is going to the left. So the magnitude is 141, but the
Negative.
vector is negative.
Negative.
Okay, now, this is 45 degrees and this is 90, so what's this angle over here?
45.
Also 45. So what do we know about b sub y?
The hypotenuse.
If the angles are both 45, what do we know about b sub x and b sub y? Gotta think geometry.
Perpendicular.
No.
What?
The angles are the same, so what are b sub x and b sub y?
Equal.
They're the same. It's an isosceles triangle. It's 45, 45.
Oh.
Okay, so b sub y is positive 141 meters, right?
Oh.
Okay, now, what do we know about d sub y then?
Then we know it.
It's 141 meters.
Okay, d sub y equals b sub y, has to be, because it's a rectangle, equals 141 meters.
Indeed.
D sub
A
X is-
is 100. We know the total length is b of bx is negative 141.
Good.
We know dx is negative 41.
Okay, so we'll write that down. d sub x has to be vector a
Minus.
minus, or
B
no,
sub x.
plus, no, minus b sub x. Okay, so this winds up being
41.
100 minus 141 meters. We wind up with negative 41,
Yeah, negative 41 meters.
okay?
I think it'd be plus bx.
Yeah, I think so too. Or we just don't call that negative, right? Meters. Okay,
Now we
So,
find
now
D.
what?
Now you have adjacent and opposite, so you can find the. Now you can find.
and how are we gonna find vector d?
A squared, square root of d sub x squared plus d sub y squared.
And so that's the Pythagorean theorem. D equals square root,
D sub x squared plus d sub y squared. And that's negative 41 squared.
what is 141 squared? What is negative 41 squared?
41 squared is 1600.
141 squared is 19,881.
All right, so let's just come up with the answer then. That's too crazy.
$146.84.
146 point what?
84, so 147.
Okay, 147 meters. Now, displacement also includes the angle. So we know how far away from the origin, from where it started, it is, but we also got to come up with the angle. So the angle will be, since they talked about north of west, we'll talk about north of west also. So that means we need this angle, because that angle is north of west,
That
okay?
is not what I got.
What'd you get?
It's right.
Yeah, okay.
So we want that angle. So I need something, some kind of trig that's gonna set up that angle. You wanna use sine, cosine, or tangent, it doesn't make any difference. Tangent?
Yeah.
Okay, so we'll use tangent.
Theta.
Theta equals, it's opposite over hypotenuse. So the opposite is d sub y, which is 141,
D.
over d sub x, which is 41. So then you need to do inverse tangent on both sides.
C sub x is negative 41.
It is, but we don't need to know that.
Okay.
In this case, we just want the angle. So inverse tangent, 141 over 41. What do we get?
73.786.
73.78, so we're gonna call it 73.8 degrees north of west. There you go, 147 meters, 73.8 degrees north of west, and we're done.